Hi, in this video I'm going to go through the answer key for week 6B poll for fall 2023. So the first question has you match the function to a description. These are just common functions that are all kind of related. They have to do with like looking at either unique values or counting those values or sorting them in some way. Some of these do a mixture of each. So the first one, columns-wise, is table. Table is a function that's really handy. I use it constantly. It simultaneously tabulates the unique values, so it counts how many of each one, as well as its output is named, which is actually really handy because it allows you to easily connect, like, all right, here is how many of which value. So the name contains the original value, and then the value contains how many of that value was in the original data. Really handy tool. The next one is order. So order is a function that I like to use to reorder information. However, it doesn't do the reordering itself, and that's the kind of challenging thing about order. It produces a vector that could be used for ordering. So for instance, if I have, you can't see that, but if I have a vector that is misordered, I send that to order, and it produces a vector that is the positions that I would want to extract in. So like if, it's, all right, let's do this, B, C, A, and I send that to order, it will return 3, which was the A, then 1, and then 2. So B, C, A becomes 3, 1, 2. And so if I use that output to do an extraction, that allows me to reorder the information. This may not seem useful at first glance, but when you think of how often we want to only analyze certain columns within something like a data frame that's much larger than just a single column, we can use that information to then reorder the whole data frame. So that's why it's just so nice. So it provides a vector of positions that could be used to sort the data set or data sets provided. It does allow for multiple arguments. Unique is the next column. Unique is used a lot under the hood, but unique just returns the unique values. So whatever the original order was of those values is just the first incidence of each unique value. So it doesn't actually do any reordering. It just removes duplicate values after they first occur. So the final one is sort, which actually does sort whatever you give it. And when it does that, it reorders the information. Sort and order obviously are quite connected. Sort does ordering, but it only just works for its input data. So oftentimes someone wants to, say, sort a data frame, and they will send it a single column, and yeah, that column gets sorted. But that column was just like a single container. And so if you sort a single container without sorting everything else, you've broken the connection between rows, which can actually be quite dangerous in terms of an analysis. It's easy to mess up there and just kind of break that connection and break that data frame and just have to start over. All right. Next up there were some descriptors of grep, grepl, and gsub. So these are all functions which do partial string matching, which makes these last 3 rows pretty easy. They all use a form of pattern, like descriptions, called regular expressions. So if you don't remember what that is, like whenever I'm saying dot represents any character and asterisk modifies the previous character so that it's repeated 0 or more times, that's the concepts in regex. That's how we write these patterns. So they're all able to do partial string matching because they all use regex. They all use regex. None of these do only like whole string matching. So an example of whole string matching would be like equals equals. The left side has to be exactly equal to the right side. There's a lot of other examples as well. The table function actually under the hood does matching. It says, all right, here is each unique value. How many match exactly that value? There's also a function called match, which does this. There's a lot of functions that do whole string matching, but these are three very powerful tools because they use regex. Power, though, has some caveats. We'll come back to that. But grep is, of the three, the one that returns a vector of index position. So wherever a match occurred, so if it positioned like 1, 5, and 7, it returns 1, 5, and 7. If, again, at 1, 5, and 7, grepl doesn't return positions, it returns logic. So it would be true, false, 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 true, false, true. 1, 5, and 7. I didn't manage to flick off the camera, so bully for me. Is that a problem? I don't know. It was a concern in the moment. gsub is a different kind of system. It's not just searching for matches. It's searching for matches and then replacing them. So grep with substitution. So it finds a match. Anywhere it finds a whole match, it replaces it. Now, if there are multiple matches in the same spot, there's a bunch of rules to handle that, and I think that might be the next question. Not yet, but we'll come back to that then. So this next question is doing some gsub, but just to kind of clarify everything, the first one is clearly a character vector. These next two are character vectors. You just kind of have to have learned that at this point. The output of gsub, since it works on character vectors, and character vectors specifically, the output remains a character vector. It doesn't get automatically coerced. So this one will actually become, so here I have a dot followed by any number of those dots. So that is any character, any number of times, including 0, and then followed by an underscore. So that occurs here. And then at this point, there's no more underscores, so you can't have any additional matches. So therefore, all of this would get replaced with nothing, leaving you with 1, 2, 3, 4. So the first value of vec2 is 1, 2, 3, 4, but it's still in quotation marks because it's still a character vector. And if you just didn't know that, you just kind of have to have memorized that. It doesn't do any sort of automatic coercion to a different character type. This one does the opposite. It matches an underscore, then any character followed any number of times. So a underscore followed by any character, 2, 3, 4, 4 times, is a match. And so that gets replaced with nothing, leaving you with chr3, which is quite clearly a character vector. Of the three of those, though, only this one ends up being able to be coerced into a numeric vector without creating missing values, and that's because 1, 2, 3, 4, just those 4 characters next to each other, can be coerced into the number 1,234. Same for this side. And this is just more conceptual. The reason why I show these examples is there are very common ways to write things like snip marker names, which is like what I work with a lot, but just having this sort of delimited data, so the underscore is a delimiter, it limits, it shows where the limits are between different concepts. This is just a very common way to represent different types of information. So marker vector, being the marker name, is the chromosome position value. Vect1 ending up just chromosome 3, chromosome 16, those are the chromosome values. And then finally, position being 1, 2, 3, 4, and 5, 4, 3, 2 is the position values. And that's just more, did you learn from that variant data set? So this next question was kind of fun. I was really, really pleased with how many people seem to have understood this, because I mean, this is a big question. Like whenever you are doing data cleaning, you have a lot of strategies you have to kind of decide between. And sometimes the strategy is like, I need the flexibility because I just don't know what someone's going to have put, and there's just too many for me to list out, or I just need the script to be flexible enough to find different scenarios. But that is often dangerous. Like in this example, if I was searching for LUE to represent blue, well, there's other kind of concepts that might incorporate blue but aren't the same intent. So that's why I say here, the goal for cleaning in this scenario is to standardize descriptions without changing the intent of the submitted value. And so I'm defining there what my goal is. Sometimes it may be to just simplify everything to a small number of categories, but I'm declaring in this example that's specifically not my goal. So like navy blue should remain navy blue. Light blue should remain light blue. And so using this is a great exploration strategy. It turns up these different values. But if I'm trying to clean it, like I probably want to use more of this whole string matching technique. So like light blue gets replaced with a specific version. It's 1 and 1. It's got to be a whole string match. And this is just an example of a very common tool. But like I said, I was quite pleased with how many people did well on this question. Great job, guys. Sorry, still a little bit sick. So the next question is doing a gsub, where you are trying to replace this and the underscore, but nothing afterwards. The problem is both sides of this. So this is going to be something like ranges for deletions or something like that on different chromosomes. This kind of looks more like a typo to me. I mean, I specifically put it in here because I thought it'd be a fun challenge, but in reality, I don't know why this would occur, but there you go. So in this case, how would I remove this chromosome descriptor despite there being 2 underscores? Well, I've already shown you what the correct answer is, so let's walk through why that is. So if I just start from the beginning to the end, CHR, CHR. And then dot asterisk, so dot is any character, and then asterisk is 0 or more times. So 0 or more repeats of, I don't need anything to reach an underscore. However, there is an alternative for the same string. So I could do CHR, and then I could do any character. Underscore is one of those any characters. Do another character, another character, another character, another character, and then there's another underscore. So this, what I'm highlighting right here, and then all the way down to the second underscore, both of those are matches. Well, an asterisk, like this right here, would be a greedy match. It means that it would just, of those 2 options, it takes the longer one. However, the question mark modifies the asterisk to make it lazy. And so for the asterisk, instead of repeating 1, 2, 3, 4, 5 times, it can just modify that period to repeat 0 times to allow for a match right here. So that is the lazy approach, and that's what the question mark does. It makes that asterisk lazy. So adding the question mark means it selects this first match, the shorter one of those 2 possible matches. So hopefully that explains it. Lazy versus greedy is a subtle difference, but it often comes in use. So this next one was really, it's a very specific question, but it's also a concept that just confuses people. It confuses everyone. But here's the behavior, is that whenever R is returning data from the inside of a function, that data is going to go somewhere. I think the term we kind of came up with by the end of the day was loose data. So right here, it returns the value of 2 from the inside of the function. But that data isn't loose in this sense. It's going to be assigned to this out object. And so that's like it not being loose. It's being used in some way. And so the only thing that ends up getting printed is what this x, this print of x actually resulted in. So in each case, every time we run this function, 1 is going to get printed because I keep sending the value 1 to x, and so it just keeps getting printed here. The question ends up becoming, is 2 going to get printed? So in this next one, it does, because I do that whole process again. X gets printed in the process. 2 gets assigned out, and it does not immediately get printed. However, then I just invoke out. And so that is kind of just loose data. I'm invoking the values inside of out without telling R what to do with it. And so the default behavior under that scenario is for R to print out. At least that's what it does with a numeric vector, which is what out is. And so it gets printed. So this would be, you would run this, and then you would see like right in between submitting this line and submitting this line, you would see it print out this value. Then after submitting this line of code, you would see it print out this value. This one kind of puts some of these concepts together. So submitting 1 to the function causes x to be printed, so 1 does get printed. And then afterwards, you're returning 2 to the user, but the user hasn't told R what to do with it. It is loose data following this term that we came up with. And so R is going to do something with this loose data, and most of the time, so with numeric values specifically, it prints that data. So both will get printed. So this next one's a little bit tricky because I am calling the function. It contains an object called y, and what I want you to think of is that y is internal here. So this is the internal version of y. This is the internal version of y. And then this is the external version of y. If you think of it in those terms, like, all right, I'm really paying attention to the environment in which an object's being created, you then are just evaluating this line of code. So if I am outside of the function and using the function, then calling y means I'm calling the external version. At that point, you then just have to decide, all right, well, where is that value going to go? So the external value is 10. And so that 10 will be applied to the first argument because it is not currently assigned, and that is x. So x becomes the value 10. Y remains its default value, and so you get this math. So 26. Quick maths. So the next one is a little bit easier. 5 is being sent to the first argument, which is just x. So x becomes 5. Y remains its default value, so you get 5 plus 16. 21. Quick maths. No, I just missed it. So this last one is a little bit trickier because you have to be able to like notice this difference between the external y here and the internal naming of an object. So whenever you're writing an argument this way, what you're actually telling R is inside of this function, create an object called y. That's what you're telling it. And so that's what happens. So you're creating an internal version of y. You're not using this external version. That's one of the few times like this that's not a few times there, never mind. That's how this works. This is creating an internal version of y. And this is using that external version of y. The difference being this one had an equal sign, and that's just how you assign internal objects to a function. This one is just y without a name, without any other indicator. That means that it is R accessing the external version of that object. So y becomes 2, overriding its default value. User always wins. And then y, which is 10, becomes the value of x. So this becomes 10 plus 6. All right, this next one is using a simulation. And let me see if I can fit this on the screen a little bit better. There we are. Using a simulation where I am sampling 1 through, you cannot see my screen, 1 through 80,000. So these are simulating 80,000 loci. This would be similar to really my first big research project where I was sampling about 80,000 restriction enzyme sites. Actually, I was sampling about 40,000 restriction enzyme sites, but the upstream and the downstream sequences are fairly independent, and so they kind of act as separate loci. interestingly enough. So I would sequence those little fragments of DNA, about 80,000 total fragments. And I would try to sample them about 1 million times each. Now that was something that I would kind of strategize around. So I would include enough samples based upon the size of the sequencing device. So a bigger sequencing device could hold more samples, but I would try to average it out to about 1 million reads per sample or more. So that's what this is simulating. 1 million reads of these loci. And then I'm calling the table function to calculate, well, how many of each of those positions had been drawn. So like if I drew position 80,000 5 times, the depth would be 5. I'm then setting up an object called min_depth, which I use to just kind of cancel out loci that did not have a correct minimum depth. So anything less than minimum depth, less than 6, gets turned into missing data. This is actually a really common strategy because, especially in heterozygous systems like the one I was working on, I would require a certain number of observations, originally 3, and then I started to move it up to 6 because if I know I have a heterozygous state, then I need to observe it multiple times. I have to observe it at least twice to even have a 50% chance of having seen the heterozygosity. And that's because the other 50% of the time I either see homozygous of one version or homozygous of the other version. And then that just kind of exponentially approaches 100% of the time, but it never quite gets to 100%. There's just an asymptote. So we'll talk through that math eventually. But that's why I do this depth calculation. It's really important when you're trying to make sure you've observed something accurately. So I then visualize this depth and I show how, like, since we've deleted a portion of this distribution, we can see that the mean has shifted to the right of the distribution's like original mean, or kind of like conceptual mean. Now, this isn't actually a normal distribution. This is there's a specific name for it, but don't worry about it. This is a distribution that approximates a normal distribution, but it's still count-based, and so it can never be truly normal, which is a continuous bell-shaped distribution. Additionally, this isn't bell-shaped. It's truncated on one side by that filter. And if it wasn't by that filter, it'd be truncated by 0, because I could never have a negative count value. So this will never be a normal value, although the larger the values get shifted to the right, and then like the smaller the relative size of the difference between bins are, the more and more it approximates like a true normal distribution. But there you go. That's getting a little bit more into how this deviates from a normal distribution. That all said, my question was, looking at this, if I were to simulate this distribution using our norm, what would the mean be? Well, the peak would be the mean. So my mean would be this value, which is approximately 1112, which looks to be about 12. And then this mean has been shifted above that. And if you think about it, it makes sense. The filtered data, I removed smaller values, driving that mean to the right. And that's it. So hopefully that helps. Let me know if you have any questions. Thanks.